foundation Taiwan University.
My name is Wenjin from National Taiwan University.
So, all three team leaders, please introduce your team and your team members.
Hello everyone, we are Team Webber, and we are from Qingxin High School. My name is Xu Changxin, Huang Yuhou, Yuan Yiting, Xie Song.
Okay, so in this section, we don't have to challenge the reporter, right? So you have 5 minutes to prepare your talk. Okay, so let's start. Okay, please write down the problem and the name. Please print your name. Okay, in the blackboard.
Yes. what to work with. And today I'll be recording program number 4, colored line. And this is the problem statement. When the compact disc or DVD is illuminated with lights coming from a filament length in such a way that only rays with large angles of incidence are selected, a clear green line can be observed. The color varies upon slightly changing the angle of the disc. Explain and investigate this phenomenon. And our main focus today will be on is there a range of angle where we can see a specific color on the DVD or CD. And this is the outline today. First, this is the observation. And this is the picture that we take in our experiment. First, we use a flashlight from smartphone to create continuous spectrum of visible light. And in this picture, you can see that there is a green line in the middle, and that is what we have to observe. And the green line will only be visible when there is a specific angle. And when we change the incidence angle, the color will be different, and that is what I will mention in the following page. And when the incidence angle is larger, the color of the line will be closer to blue. And when the incidence angle is smaller, the color of the line will be closer to red. And this is because of the wavelength of different colors. And for the theory, for this experiment, we try the CD and the DVD disc. And you can see that this is the surface of CD and DVD. From the surface, you can observe there are many holes, and we call it grating. And between gratings, there are some distance. You can call it a spacing or call it a pitch. So you can observe that for the size of the CD and the DVD, their grating and the spacing, the size is different. So when we use the white light to shine on the CD and DVD disc, you will have some difference. So when we shine the white light onto the surface of the disc, the spacing on the disc can create diffractions. And the diffractions can cause the wave path difference. So the wave path difference can cause the interference. So we can observe different colors of light when we change the angles. And just like what I have mentioned, when we have a large angle, the color of the line will be blue, and when in small angles, the color of the line will be red. And I will explain in the later. And this is our theory. For this picture, this is the picture that I drew. When we use the incidence angle to shine on the surface, it will have a reflection angle. So if we set the incidence angle in theta, because the incidence angle will equal to the reflection angle, so the reflection angle will be theta too. And also, we set this angle phi, so the theta plus phi equals to 90 degrees, just like this picture. And for this d is the length of the spacing. So according to the wave path difference, we need to observe the wave path difference. So from this triangle, we can know that the wave path difference is d sine phi, and so it equals to m lambda. So this m can be 0, 1, 2, 3, the whole number. So just like what I have mentioned, we set the phi plus theta equals to 90 degrees. So d sine phi, we can also write it as d sine 90 minus theta degrees. So because the incidence angle that we use is smaller than 90 degrees, so according to math, sine 90 minus theta can also write like cosine theta. So for the wave path difference, it is d cosine theta equal to m lambda. And also, for the same disc, the length of the spacing will be the same. So the d is the same. So when we change the angle, the theta will be different. So if we let the angle become bigger, the theta will be bigger. So cosine theta will be smaller. So that means the lambda will be smaller too. So that means we can observe blue lines. That is because the wavelength of the blue line is shorter. Also, compare the CD and DVD. Their length of the spacing is different. For CD, the length of the spacing is 1,600 nanometers. And for DVD, it's 740 nanometers. So when we use the same incidence angle to shine on the surface of the disc, the cosine theta will be the same. So if we have a larger length of the spacing, the lambda will be larger. So that means we can observe the red line. And this is our experimental setup. For this track, it is 1 meter long. And at the right hand side, we use the flashlight from the phone to be the light source. So also you can see there is a CD or DVD disc on the track. And when we change the distance between the CD or DVD disc and the light source, the incident angles will change. So that is what we will be observing. And these are the variables. The independent variables are the incident angles and the CD and DVD spacing depth. The CD and DVD spacing depth can affect the incident angle. And for dependent variables, that what we have to observe is the color of the line on the disc. And for the data analyzed, for the height of the flashlight, we set it 9 centimeters. And the distance, and this is the distance between the disc and light. So, and this is the angle, the incident angle, we set it theta. So, we know that 1 divided by tangent theta will equals to 9 divided by the distance between the disc and light. So, tangent theta will equals to the distance between the disc and light divided by 9 centimeters. And this is our experimental result. For this chart, it is the condition when we use CD disc. And for these colors, we observe color red, green, blue, and purple. And when at different, because they have the different wavelength, so that we use the different incident angle to observe it. And for the color red, the incident angle is 59.1 degrees, so we can observe the color red. And for the color purple, the theta, the incident angle is 78.4 degrees. So you can observe that when the incident angle is smaller, the wavelength will be bigger, just like what I have mentioned in the video. And these 4 are the pictures that we can observe. You can observe that in the middle there will be color red, color green, color blue, color purple. And this is the data analyzed from DVD disc. And so we also observe color red, green, blue, purple. And for the incidence angle, that is similar to when we use CD, but the only difference is that for color purple, we cannot observe color purple. And we think that is because the wavelength of the color purple is small, so that means we need a larger incidence angle. But when we have a larger incidence angle, it is similar to the size of the angle that we observe this picture. So we think that the size of the angle and the incident angle may be on the same plane, so that we cannot observe color purple. And these 3 are the pictures of our experiment. For the discussion, from the data chart, we can see that no matter what kind of disc we use, CD or DVD, the sequence of color that we see is from red, green, and blue. And that is due to the wavelength of this color. The wavelength of the color red is the longest, and the wavelength of the blue line is the shortest. So the color green will be at the middle. And when the distance to the light source is longer, the color of the line will be closer to blue. And that is because if the distance to the light source is longer, the incidence angle will be longer too. So the wavelength will be shorter, so it will closer to color blue. And when the distance to the light is shorter, the color of the line will be closer to red. And this is because when the distance to the light source is shorter, the incidence angle will be smaller too. So the wavelength will be longer. It's closer to color red, just like what I have said in the DVD. And for conclusion, the difference of the disc doesn't affect the sequence of the color. And when the distance between the disc and the light is larger, the color of the line will be closer to shorter wavelength. and that is color blue. And when the wavelength of the line is shorter, the incidence angle is bigger. And the larger is the spacing, the longer distance we need to see the same color light. And this is the formula about the wave height difference. And this is all. Thank you.
Okay. So, opponent, you are ready to question the report.
Okay. First is that I want to ask that your group pitch, how do you measure about it? You search it from online or you measure it by yourself?
No, because we think that for each CD and DVD, the differences of the length of the grading and the pitch won't have a large difference. But when we do the experiments, we use the same disc and also use the same DVD. So for the
No, I mean the 1,600 disc value you search from the internet or you?
we search from the internet because we think that for the CD and the every CD and every DVD disc will have nearly the same length. But when we do the experiment, we use the same disc.
So I want to ask that in your experiment, do you make a dark room or make the room have no light?
No, we have less.
Okay. And I want to ask that your observation point and your incident point is on the same point or different point.
What do you mean?
I mean that your observation point, your camera and your flashlight is at a different point, right?
Oh, well, just like the experimental setup, the flashlight is at the right hand side, and also we observe it at the same side.
No, I mean point.
Yes.
The place.
Yes. Yes.
Same point?
Yes.
Okay, I'm finished.
So, so you have 3 minutes to prepare your report. component start talking, and then maximum 4 minutes, and then discuss with the reporter.
Good afternoon, honorable judges, commissioners, and mechanics. And our problem is number 4, color design. Okay. And here is the problem statement. And they focus on the range of angle where we can see the specific color on CD or DVD. And there's theory. Spacing on the disc creates diffractions, and diffraction causes wavelength difference. And bigger spacing can create larger wavelength color. And their setup is DVD and CD. And the light source, and they have a trend. And the incidence point and the distance between the disc and the light. And the point I we just discussed is how to get the group pitch. They say that they search from the internet. And does the environment prevent unnecessary refraction? They say they don't have. And the incidence point and observation point, they say that is on the same side. And about their conclusion, the difference of the disc doesn't affect the viscosity of the color. When the distance between the disc and the light is larger, the color of the line will be closer to shorter wavelength. When the wavelength of the line is shorter, the incident angle is bigger. The larger is the spacing, the longer distance they need to see the same color line. Okay, so discuss. Okay. We just said that you didn't make the dark blue for your experiment. So we think that you didn't prevent the refracted light from interfering with your incidence light and cause errors. Do you agree?
At this picture, we can see that not only the middle line have a color, we can also see that there are some other colors on the side. And we think that is because of the light from the environment that causes.
Yes, so it may cause the error. Do you agree?
No, the light from the middle is all from the light from the flashlight. From the outer, for the outer color that is from the environment.
But can you prove that for your light source that the only light from the incidence you can't prove that your environment won't cause the error?
No, you can see that for this time this is the straight, and just like the light from our flashlight. And also because we need to photo this picture, so that we need to have some light from the environment to let we observe more clearly.
But if your environment don't have the light, you have a flashlight that you can incidences, so you can still camera.
No, but for the charts we have done, and we have shown you that is when the environmental don't have any light. And because of this picture, so we need to have the light to let us to see clearly on charts. That is dark environment.
Okay, but I don't agree with that. And the second is that you say your group pitch, your value of your group pitch is brown online. But do you think about that maybe your CD's group pitch isn't the same from the online?
Yes. Well, when we do this experiment, we use the same piece of CD and DVD. So for the distance of the spacing and also the height of the grating, it will be the same.
But for CD, some CD's group pitch is about 1.1, but some is about 1,100, and some is about 100, 600.
Yes. For that number, that means that for the length of the spacing of the CD will be longer, and that is what I want to tell you. But maybe that won't be the exact number because the number is from the internet.
Okay. And can you explain this phenomenon again?
Okay.
I don't really understand.
This is the incidence angle, and we set this angle theta.
Okay.
So the incidence angle will equal to the reflection angle.
But this is a diffraction angle. It is not the reflective angle. It won't be the same.
No.
Then
This is the. I said this is a refraction angle. I don't know what you think that is a diffraction angle.
but
Because this is on the
but
this
for this
surface,
experiment-
this sharp and this.
but for this experiment, we want to observe the thing is that the diffraction.
The diffraction causes the wave path difference.
Yes, so the angle won't be the same if it is a diffraction angle.
But it will also have the diffraction angle.
But you use one light to hit your grating, and it will cause the diffraction, not the reflect.
Yes, but for the diffraction that causes, what it causes is this wave path difference.
Yes, so they have wave path difference, so they cause the diffraction.
Yes, but for this, so do you think that there is reflection in this experiment?
I think there is a reflect in this angle, but you want to find the line that is red, green, blue, or purple. It won't be the reflect, it will be the diffraction.
Okay, that is due to the just like what I said is the diffraction.
But your diffraction angle will be the same with your incidence angle.
Why?
Because it is a diffraction angle, it isn't a reflective angle.
So do you think what angle do you think this will be?
This angle, you should have another name for it. Maybe your incident angle is theta I, so your diffraction angle is theta r.
Okay.
It will be not, so this formula, I think that this formula is a great equation. Do you
Also,
agree?
how about do you think that so do you agree that these two angles, when we plus the theta and the phi together, will be 90 degrees?
For your, this, oh, sorry, I can't really see.
Do you think the theta plus phi will be 90 degrees?
Yes.
Yes, so it can also match this. Even though the incidence angle will equal to refraction angle, it will also match.
No, but for your incidence angle, if you mean the incidence angle, it will be that this angle is the incidence angle, and this is a diffraction angle. Not this is the incidence angle, and this is the diffraction angle.
This is the trick. So do you think that this new angle will be 90 degrees?
No, answer my question. What is this angle?
This is the angle that we shot on the surface on this, and it have the reflectors. Yes, just
No, but if you want to say that this is the incidence angle that you hit, if it hits the refraction angle, it must be this angle, not this one. Because for this is already that is projected. Or this line is line that you already reflected it.
yes.
It is
From
not
this chart,
incidence.
I just want to tell you that this angle will be 90 degrees, just like this. So
I know this will be 90 degrees.
so it can match these formulas.
But this is not the incidence angle.
This is not important for this formula
Why?
because these two angles will be 90 degrees.
So this formula doesn't have any. Can I see? Is this a gradient equation? This formula. Is this a gradient equation?
Rating
Gradient equation.
what?
I use blackboard. This is a gradient equation. Sorry. This is a gradient equation. It's your left equation from the gradient equation. In my opinion, your formula is from this gradient equation.
Our formula is from the formula of the wave path difference.
This is the wave path
Yes, so
difference.
that is it.
So that is the same. So now I'm talking about this angle and this angle won't be the same. These two plus together won't be 90 degrees.
So what do you think it will be?
If you say that your incidence point and your observation point is on the same side, so we can move it into sin theta and equal n lambda divided by d minus. Sorry, let me think about it. I think it will be like this.
Okay.
So, this formula, I think that it isn't the correct formula. Do you agree?
Okay, agree.
Okay. So I just say that your group pitch, maybe it won't be the correct group pitch of your experimental equipment.
Yes, that would not be the exact number, but what we use is the same piece of disk, so it will be the same.
No, I mean that for your theoretical data, you will calculate the sin theta. So if your group pitch is round, your sin theta is round. Did you agree?
Yes.
So I think that maybe if you calculate the theoretical data, it is not the correct data.
Okay.
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 And the second question is that. The second question is that how to define the line, the color of the line.
Okay, from starting our 50 centimeters, we can observe color red. And from starting our
No, I mean that. Why do you say that color is red?
from your observation.
Okay, from your
You can
observation.
observe every color because of the interference. But mostly we observe color green. That is because the color green is a completed construction interference.
Okay. In my opinion, I think that you define that color by your observation isn't so correct. Maybe you should find a way to see that. Maybe in this picture, this green line's wavelength is how much is your wavelength? Did you agree?
No, we didn't record the wavelength.
Okay. Okay. I want to ask another question. For your experiment, I assume that there is no error for your environment and that is not from your flashlight. You don't have another light from your flashlight. Then we know that the whole path of CT is the whole gray distance. I'm sorry. Your CT is full of grating. Do you agree?
Yes.
But why can you just observe a line, not whole green, not the whole CD is a green?
Because we shot on the one spot on the CD.
But your light is flashed on the whole CD.
Yes.
So why can you only see the line in the middle, not the other side?
No,
What
because
do you think about it?
that is from the angle from the direction you shot the flashlight.
But for your flashlight, it is a line like this. So if on the CD, it will cover the light will cover your CD.
It
But
is
you
a
can
straight
only
line.
see the diffraction on the
It is a straight line. Straight
You
line.
say you use a flashlight.
Yes, but I just want to let you know that that flashlight is just for this experiment, what we use is just a white light because it is a polychromatic light.
Okay. And have you ever tried another angle for the theta that CD can see?
Yes.
Have you ever tried? Maybe in 90 degrees that you can see a red line, but maybe in 40 degrees you can see a red line. Have you
Yes,
ever
there
tried?
is a range of the angle. So this is the starting distance when we do this experiment. So from 15 to 22, there will be like from color red.
Okay, time is up. So the opponent, please summarize the discussion.
In the discussion, we have talked a lot about maybe like how do they define their color of the light? And they say by observation, but in our opinion, we think that it isn't very correct. And the grating equation that they use and they use to calculate isn't correct. So we think that if they do calculate their theoretical value, the theoretical value won't be correct. And for their environment, we can't agree that there is no there is no reflected light from interfering with their incidence light and cause error. We think that maybe there will be an error. Maybe there is a white wall and your light hit the white wall and you reflect the white light. So we think that maybe it will cause the error. Okay. Thank you.
Okay, review now is your turn.
Okay. First question I want to ask opponent. What's the main parameter in this experiment?
In this experiment, what does it really matter? I think that it really matters on the observation angle. Their observation angle.
Yes. People do agree with her.
Incidence angle.
Yes. Second question. Opponent, do you think the result of the TBD and CD is different?
Maybe they will have the same trend, but their result won't be the same.
Yes. Reply.
They will be similar. When we have a bigger incident angle, we can observe the color is color blue, and a smaller incident angle is color red. Yes, similar.
Okay. Opponent, how to define green light or any color light?
We have a software. We got a software called ImageJ. We took a picture of the CD that we have the diffraction rewind, and we put the picture in ImageJ, and it will analyze the lambda of our rewind. So we can see the green lights. Maybe the lambda of it is 495 to 570. So we divided the green line.
Okay. Reply. How do you measure your CD's incline angle?
Incline angle.
Yes.
Incident angle.
Your angle to this incline angle. Okay. Opponent, do you think the incline angle, when the incline angle is bigger, what do you think will affect the results?
Sorry, can I ask what is the incline angle?
This angle between the disk and the plate, your desk.
But I think that in their experiment, they make the plane and the disk on the same angle. They didn't have any change for the disk. And if they change the angle of the disk, it will change the incidence angle.
Okay. Reporter, do you consider the angle between light source and observer?
For the angle you said, it will also influence the incident angle. So what we measure is the incident angle.
Okay. Opponent, do you think it will affect the results?
What will affect the result?
Okay, time is up. So reviewer, please prepare your report. Okay, so we will please give a presentation.
Hello everyone, I'm a reporter from Faculties. Okay, I'm going to review. Okay, this is the problem statement. I have some key points. It's a complex DC DVD, and a green line can be observed, and the angle of the disc is the key point of this problem. Okay, this is all lines. The report course is well explanation of 30 phenomena and great experiment data and analysis. But we don't have the quantitative comparison between theory and experiment, and words too small. The observation picture is not clear, and define the color. And lack of a theory in this formula. The time management is poor. The opponent's process get a light error correct, and context the word is not clear, didn't talk fluency enough, talking about the angle is didn't too much. And the opponent can talk about more another question, and talk about more parameter. Okay, it's a pure question. First, opponent asks, is there experiment in the dark room? The reporter says no. And in my opinion, I think if it didn't in the dark room, it will have many errors. It will cause. Okay, opponent asks to measure the length by yourself. And the reporter says search on the internet. I think the reporter should use the microscope to see the length of that by himself, because it will be some difference from different discs. Okay, this is can you explain the formula? And the reporter said resist the angle is correct. In my opinion, I disagree the reporter talking about. And I think the reporter should do more experiments about the wavelength. Opponent asks, have you ever tried the another angle? And reporter said yes. But in my opinion, the data is not enough to correct his problem. Okay, this is a real question. What is the main parameter of your experiments? And opponents and the reporter both says inclination. And how do you measure the inclination of the disc? The reporter didn't answer. Does using DVD or CD affect the results? Opponent says not the same. And the reporters answer similar, but I agree with the opponent's answer. Okay, how to define the color of the line? Opponent says software. I asked to consider angle between the source and observer parameter, and in my opinion, it will affect the result of the experiment. So it will be the main parameter of this experiment. Thank you.
Okay, so reporter, please conclude the remarks.
This is what I have mentioned. A specific length of angle to corresponding colors. The green line will be visible in a specific angle. Also, larger when the angle is larger, the color will be closer to blue because of the wavelength difference. And the variables are the CD and DVD disc and the incident angle of the light. And the diffraction causes the different color paths. Also, the distance of the light source increases, wavelength of the light decreases. From opponents, they do pitch sources from the internet may be different from ours, but the comparison between DVD and CD is the same. What we have to For the information from the internet, what we have to tell you is that we just want to tell you that for the CD, the grading will be longer. And that is just what I have to tell you, even though we didn't measure the correct number. And also, we turn off the light to observe the phenomenon, just like the charts in our presentation. But we open the lights just because to take the picture for us to observe. So you can see there are some other colors on the side. That is caused by the outer light. Also, the incident angle and the diffraction angle of the specific color reflected might be a difference. However, our dependent variable is the incident angle, so that is what we focus on. Just like from what I said, that is a little bit arrow wise. Our main focus will be on the yes. And just like what the reviewer has said, we can calculate the incident angle because we can know the height of the flashlight, also the distance between the disc and the flashlight, so we can calculate the incident angle. Yes. And also the observing angle will affect the result, so what we measure is the incident angle. Yes. Thank you.
Okay. So now question from the jury. Yes.
So the photos will show the experimental setup. Show the experimental setup.
Okay.
So where is the then?
The light source is from here.
Okay. So according to the problem statement, it says that only rays with large angles of incidence are selected, right?
We think that the
So how do you select only the effect from the large incidence angles?
we think that different color will have different specific angle. But if the angle is like too big or too small, then for the wavelength is not what we can observe.
No, I'm asking how do you select only large angle of incidence?
No, we didn't select only large angle. We
Okay.
think that
And
we
then the
have
opponent, how do you select only large angle of accident incident light?
We have the gradient equation. We put our m lambda z and
Just everyone can write, you can just draw your experimental setup. How do you
okay.
select only large angles of incident?
In our experiment, we put a disc here, and we make a diagram by a box, and maybe the light source is here, and the light angle will be here.
Okay. And then the review.
Okay. Here is the bar, and our CD is here, and it's inclined. And here is the light source. We use the light, and we can observe the light on the disc.
Yeah, but you actually have all the angles, right? Your lights actually comes from all the angles. But the problem says that you only need to select the large angles.
No, this light is a straight. It's not the fresh light. It's the like the LED, but the light goes straight.
Okay, that's fine.
Okay. So I also have 3 questions for all 3 of you. So first one, could you please go to the surface of CD? Yeah, you have a slide about the surface. Oh, okay, here. So if you look at this, okay, this profile. So those dates, okay, you got several dates, and then relate to the binary number, okay, like a 0 and 1. So the distance, the width, and the distance between those dates are different, right? Yes. Okay, so how could you model those stuff? Because could you go to your theory? You have derivation. Okay, you have derivation, right? Yeah. So in this part, you have a very regular state here, right? And then you have very regular distance. So my first question is, this model is correct or not? Okay, for all three of you. And then, second question, here you assume the source, the light, is coherent, but the filament is incoherent, which means the phase between different spots will be different. Now, how could you have this relationship? Okay, because now the initial phase will be different. This one based on the same. Okay, for example, this part, you got the same phase. Then you have interference, constructive interference at certain position. Then you see a green light. Okay, based on this. But at the beginning, if this is an incoherent source, then you don't have this relationship. Okay, that's the second question. And then third question, could you go to the observation? Okay, look at here. This is not a pure green light. Okay, this is not uniform. The color is not uniform, right? So in your model, you cannot explain why the color is not uniform. Okay, so let's, three of you, please answer the question.
Can I go first? Can?
No, sure.
Okay. For the first question that we hope our disk is like that. So we use Python to write the data that we want to put it into the disk. And let the gradient of the disk is 10, 10, 10. We make the disk maybe like 10, 10, 10, 10, maybe regular.
Yes, but in reality, for every CD, it's not regular. It's never regular, right?
Right.
Yes. So.
For this, in our opinion, we think that for this phenomenon, it's just looking for the white light heterogeneity and make the wavepath differences. So we think that it has a little different. It doesn't matter a lot.
Okay. Because the CD is 0101, can I use the blackboard? Yes. Okay. So this surface is more like here is the short distance and here is the longer distance. And when the light goes this, you will have two different lights. If the distance is short, you will have this, and if the distance is long, you will have this. So we observe the light is a mix of this light and this light.
But how can you have two lights? You have a lot of data, so you can have any possibilities, right?
So we finally observe the light is the mixture of this and this, the short distance and longer distance.
But how come you can not see other light?
Not see other light. Because
It's fine. Just quick answer.
not other light is because other light is not obvious.
Okay, so reporter, do you have any?
For the first question, like you have mentioned, because of the recorded, so for the distance will be different. But I think we think that we have a better solution next time is that we can try to turn the things and then find an average. To find an average. Because the distance must be different because it is recorded. So we try to decrease the deviation by
How?
turning the things.
You cannot print every CD in the same way. 没有，它好像是说可以延长，对不对？OK。Then go ahead.
The second question in our explanation is that just like the theory that we have to, it is the ideal condition. Yes. For theory, this is the ideal condition.
That's fine. So we are out of time. So maybe just prepare our score. Okay, so please raise the score. We got a 6, 5, 4, 6, 6. Okay, now the score for the opponent. 6, 5, 5, 7, 7. And then the score for the reviewer. 6, 6, 5, 6, 7. Okay. So just switch. So reporter, please prepare your presentation. Oh, okay. So print your name. Okay, print the name of presenter, please.
这样没办法控制吗？
可以。
Good afternoon, various components and their containers. I'm one share from D5. The topic I'm going to present today is problem 12, rice paradox. And this is a problem statement. Take a vessel and pour some mineral material into it, for example rice. If you dip a spoon into it, then at a certain depth of the immersion, you can dip the vessel and the contents by holding the spoon. Explain this phenomenon and explore the relevant parameters of the system. And our main focus, first the relation between depth and the maximum static friction. And second is the relation between diameter of the vessel and the maximum sticker friction. And third is about the relation between diameters of silicon dioxide and the maximum static friction. And this is our demonstration video. And we first push our rice in a tight situation, and we heat the stick slowly into, and we push it again to keep the situation in tight situation before we measure about the force. We pull it slowly, but this video has speed up already. And this is an experimental setup of equipment. And for our material of our vessel and the rod is the same. We use pretty pointer to make it so the material of it is both PLA. And for our general material, we use selection dioxides. And our first diagram, for force A and B is a static friction between the rod and the selection dioxide. And for force C and D is a static friction between the silicon dioxide and the vessel. And the F, if we view this picture for just a rod, the F will be mg and the m value and the m is the mass of the rod plus Fa. And if we make our silicon dioxide and the vessel in the same distance, that the F is the mg and the m is the mass of the rod plus mass of the vessel plus mass of the selection dioxide. And this is our phenomenon explanation. For our phenomenon explanation, we define that the vessel and the silicon dioxide are on the same systems. And according to our first diagram, F provided the force to lift the whole system up, including the vessel. And for B, if F is smaller than the gravity of whole system, the system can't be developed. And if our F is bigger than the maximum of Fa, the system cannot be developed. And this is a theory. For our P is a pattern that the silicon dioxide gives the rod, and R is the radius of the rod, and H is the depth of the insertion, and K is the conversion of coefficient. And for our experiment. And for our experiment method, first we pour the selection dioxide in a ladle and press it into a tight situation. And we use a hammer to strip the rod in and press the selection dioxide in. And we use a vessel with a hole to press the selection dioxide to make it a tight situation. And we use a cotton straps to link the force sensor to pull it. And for this experiment, we'll get two situations. First is that we can dip out the whole systems, so we'll get the maximum static friction. If we can dip whole system, we'll keep applying the force until the system grows. That means that the force can dip the whole systems, and we'll get the gravity of the whole system and the maximum static friction. And this is our analysis method. For this is the force sensors use method. And this will be the maximum static friction. And for our hypothesis, first is about the diameter of the rod is 1 centimeter, and the diameter of the vessel will be 3 to 7 centimeter. And for the diameter of the silicon dioxide will be 1.5, 3 millimeter. And the density of the silicon dioxide will be 1,600 kg per m square. And this is a static friction convention of the theory formula that we use to calculate. And for our experiment 1, and the independent variable is the depth of the rod, and the dependent variable is the maximum static friction, and the controlled variable is the 3 millimeter silicon dioxide and a 3 centimeter vessel. And for our hypothesis, the depth of the rod is positively correlated with the maximum static friction. And here's the result. For this chart, we separate into 3 sections. For section A, we can't do the systems. We can't leave the system because the force is bigger than the maximum static friction. And for section B, we can't leave the system because the force is smaller than the gravity of the systems. And for section C, that we can leave the system, and the area of C can indicate the difficulty of the pulling the systems. And for our experiment 2, the independent variable is the diameters of the vessel, from 3 to 7 centimeter. And the dependent variable is the maximum static friction. And the controlled variable is 3 millimeter silicon dioxide. And our hypothesis is that the diameter of the vessel is negatively correlated with the maximum static friction. And here's the result of the diameter of the vessel is 3 and 4. And the blue dot is an experiment data that we do. And the gray dot is the gravity of our whole system. And as we can see that the bigger diameter of our vessel is the K, the conservation coefficient is bigger. And this is the data of diameter of the vessel is 5 and 6. And this is the diameter of the vessel is 7. And here's the result. When the diameter of the vessel is smaller, the curvature is bigger. And it means that it can leave a bigger weight. And when the section C is smaller as the diameters increase. And it means that it's influenced by K. It means that K is bigger. And for our experiment 3, the independent variable is the diameter of our silicon dioxide from 1.5 to 3 millimeter. And the dependent variable is the maximum static friction. And the controlled variable is the value of the silicon dioxide. And for our hypothesis, is that the diagram of the silicon dioxide is negatively correlated with the maximum static friction. And here's the result of 3 centimeter of the 3 centimeters diameters of the vessel. Sorry. And the difference between them is that the diagram of the silicon dioxide is in the set 1, 1.5, and 3. And as the diameter of the silicon dioxide increases, the K will be bigger, and the C will be smaller. And this is the diameter of the vessel is 4. And as we can see that for our experiments and for our experiment, the experimental value and the theoretical value is very fit. And for the diameter of the vessel is 6. And for 7. And here's the result. In different radius of vessel, as the diameter of the silicon dialysis increases, the K will be bigger, so the C will be smaller. And the difference between the line of free silicon dialysis is bigger, and the K range will be bigger. And here's the discussion. First is the influence of K, that is the diameter of the vessel. For delta X is the influence range radius of the rod. And maximum delta X, delta XA, and the maximum delta XB is the maximum compacted length. And as we can see, that XA is smaller than XB. So we can know that if X divided by maximum XA will be bigger than X divided by maximum XB. And so we can know that this will be the law of this experiment. So we know that the smaller the diameter is, it will be tighter. And the K is smaller, the diameter is smaller. For our maximum stick diffraction of the smaller diameter is bigger. And here is the second discussion. It's the influence of K, that is the diameter of the silicon dialysis, and X is the same. And so we can see that the smaller diameter is tighter. The smaller diameter will be tighter, and the K of the smaller diameter is smaller, and maximum Fs is smaller. The diameter is bigger. And for our conclusion, that the rod is positively correlated with our maximum stick diffraction. The diameter of the vessel is negatively correlated with our maximum stick diffraction. Diameters of the silicon dialysis is negatively related with our maximum stick friction. That is proof that our hypothesis is right. And the area of C can indicate the difficulty of pulling the distance. And the value of K is relative to the diameter of the vessel and the silicon dialysis. Thanks for listening.
Okay. So, opponent, please question the reporter.
Well, in the report, I'd like to ask a short question for your conclusion. So first, what's your main parameters of your experiment?
We have changed two things there. First is the diameter of ours. Is our diameter of our silicon dialysis, and the second is our vessel. The diameter of our vessel.
Okay, so the problem statement says that they use rice to show this phenomenon. So why did you use silicon dioxide?
So in our opinion, silicon dioxide is more like a circle. So in the calculation, the error will be slow, more small.
The problem statement states that they use rice, and rice is not a circle. So do you think that your conclusion will correspond to the conclusion that the problem statement wants?
We think that our experiments won't cause a lot of error because it's for using the collision axis for us is just easier for us to do the calculation.
Okay, I'll discuss it later. And so why did you press the silicon dioxide in your video?
We want to make the first press is for the beginning situation. We want to make it tight. And the second is because we hit the stick in, so we want to press it again to make it a tight situation.
So how many times did you press?
2 times. Yes.
So is your force of pressing constant every time?
For us, we just press into most tightly situation.
So how did you know that is the most tightly situation?
Because we can't press it anymore.
Okay. So, you have 3 minutes to prepare your report.
Tigers, and today I want to discuss about rice kettles. So the problem statement is that you just pour some granular material and into a container and just dip into a certain depth, and you can lift it, and we need to explain this phenomenon and store resonance parameters. So that's a summary of reporter and the pros and cons. So the observation here is that they just show the videos in the past period, and the pros is that clearly shows the phenomenon. But the cons is that we don't know why they should press the container flow 2 times, which we will ask later. And the parameters discussion is about the size of vessels and the size of the silicon dioxide and the depth. So pro is that there have complete parameter discussion, but the cons is that they cannot give any data. And in theory, and the reporter just used force analysis and an integration to give the formula of the rice kettles, but the reporter lacks explanation of the equation, the integral equation. In the experiment, they use force sensor to set up and use many graphs to show the results. And we think that that clearly variable mention is very good. But there is no comparison between different parameters. And the error bar sometimes is just too big. And the conclusion is that the reporter gives only a qualitative conclusion, a lack of quantitative conclusion. So, which we will ask for the quantitative part later. And here's my opening question now. I want.
Okay, so you can make a discussion.
Okay, so I'm gonna continue the problem I just asked. So did you consider the shape in your theory? Did you consider shape of the rice or the silicon dioxide in your theory?
Because in our opinion that the problem statement that said that you want a linear material, for example, rice. So for us, we use silicon dioxide is for easier to calculation. We think that it won't have a lot matter for the result of our experiment and theory.
Okay, so if you change silicon dioxide into rice, what result can you expect?
We think that maybe there will be more error because for rice it's not very good to predict the result. But for our silicon dioxide, it's a circle, so we can predict its result.
So can you predict this result in your theory?
Yes, we have the vertical line and the.
No, I say in your theory.
Here. For this is our formula to calculate our theory.
Okay, so now my question is to ask, what is the dA of this integration formula?
It's just a
Contact area, or it's just the area of the vessel.
it's a force formula.
Sorry, it's just
PTA is a formula that used to calculate.
But as you know that you use silicon dioxide. So may I use the blackboard? So in your theory, you consider the silicon dioxide to be like this because the contact area is just use PDA, and you did an integral shows that you consider it as a continuous
contact surface. So could you, but the actually conditions like this. This is use silicon dioxide walls, and so how can you use integration to this condition?
So this is the reason that we use the silicon dioxide. But if we use rice, it will be hard to make our theoretical formula because rice maybe will be like this, and it will be hard to calculate. So we use silicon dioxide is because that it will be more, the error of the calculation will be more small.
But the contact surface, the contact area is still not continuous. So you cannot use an integral to calculate this.
So we
So
have,
simply, so could you do some correction to this formula?
so we have a conversion coefficient. So we have a conversion coefficient there.
Did you measure your conversion coefficient in your sphere?
Okay, it's okay. K here. We put the K here because that it is a conversion coefficient for this error.
So how can you, so I believe in different diameters of the silicon dioxide, I think the conversion coefficient is not the same. So in your practical part, how do you measure the conversion coefficient?
For conversion coefficient, we put our experimental value back to here, and we calculate back for K.
So you assume this formula as a right formula?
Yes.
Did you expect the conversion coefficient to, do you think that the conversion coefficient in the same diameters of your silicon dioxide to be the same?
Because in our
No, just told me
Yes.
same or different. So could you show your experiment data? So I think the K you have mentioned is about the conversion coefficient, right? So could you show us? So this is 0.15 by average, or did you just did only one?
average.
By average, how many experiments did you did for every condition?
For every kind, like this part we have nine.
No, I say in the same condition. Because
This is the same condition.
yeah. So how many times did you do to plot this graph?
45 times.
45 times. Okay. So did you use all of the data?
Yes.
Or you use all of the data?
This the design that is really.
So how is what is the main reason that called big deviation to your experiment, your 45 times experiment?
Because we think that for this phenomenon, it has a lot of reason that will cause error. So we do a lot of time to prove that.
So I will consider, but I will suggest that the reporter should do the theory more precisely in order to calculate the K more persuasive. And could you show your other experiment? Okay, so like this. So why is so you will expect the K to be the same, right? In the three groups.
No, it won't be the same.
So why is the first one and the second one almost the same, but the third one become more larger than this one, since that there is only the diameter is
For K, it is only a percentage. So in our experiment, this is the percentage that this error won't be happen. So we can say why we can let it be in a trend or something. It is the real data that we calculate out.
Does this fit your theory, or you just calculate on your theory?
We calculate from our experiment.
So you get a K out of this. So what conclusion can you get with this coefficient?
As the diameter of the silicon dioxide increase, K will be bigger.
How will this affect to the phenomenon of
bigger, the section of RC, that means we can dig holes and up, will be more.
Easily. Okay. So why is the one with 3 millimeters diameter with a larger case?
Because in our experiment, this is the,
Did you think 3 groups of diameter is enough to stay your problem? To stay.
no, we have a done.
But you just only consider 3 diameters of your silicon. So do you think this is enough to stay your problem? And just in this one, the 1 millimeter is just the case 0.5, and this is 0.55, and this is 0.1. Could you explain why this K is different from the last picture? So this one, 46, 47, and 75, and last the third, 22. Yeah. So 4, 42. So why would you? So why is that 0.1 K existing?
Because the equipment that we do our experiment in the sense, for this free, we use the diameter of the vessel is 4 cm, but for this is 5 cm, for this is 6 cm.
So why is the K much smaller than this one? Not corresponding the trend in the page 23, 22, and 23. So why C will be smaller?
C will be smaller.
If you say that as the diameter of silicon increase, the K will be bigger, and you just say C will be smaller. This is just not matching.
This is our hypothesis. When we are doing the experiment, we found that it is so. This is our hypothesis, and for this case, it's a percentage. We can't really prove that it will be like a trend or something.
Okay. So I would like to do this problem. So I'm going back to the problem of pressing. So you use hand to press the.
We use another vessel with a hole under.
What does it look like? Could you show your
Here.
So why did you? So you just insert the rod and then just compress with the vessel, right?
Yes.
All right. So if you compress with the vessel and then insert the rod, so will the conclusion be different? Will the results be different?
When we press the silicon axis, we won't move the rod.
So did you press it first and then insert the rod?
We press it first, and we stick in the rod, and we press it again.
So you say you press 2 times, so you just push 1 time and then insert and push the second time.
Yes.
So the first question I'm going to ask, how can you make sure that your rod is perpendicular to the plane? Do you know what perpendicular is? Between 90 degrees.
We can't really measure about that, but we'll do our best to that it be 90 degrees.
Okay, time's up. So, opponent, please summarize the discussion.
In our discussion about the theory and experiment of the recorder's presentation, we discussed about the theory of that integrating formula, and we discussed about the K, the coefficient. And in the experiment, the K seems to be bigger when the diameters of the silicon dioxide is increasing, but one group is not matching. So we're wondering why and how the K will be affected. And the other part is asking about the silicon dioxide shape and about continuously about the silicon dioxide. And I didn't agree with that integration formula because we can just correct it by only a K, a constant, and not by other. Okay.
Okay. So reviewer, now it's his turn.
Okay, I want to ask that what if the size you use for the granular, and then you add a smaller size into it and mix them together, will you think the friction of them will be higher or lower? Sorry, can you the size you use and you add smaller sizes of balls into it,
No,
do you think if you mix them together, will the friction be higher or lower?
I think the friction will be higher.
Okay, what do you think? Okay, and what do you think there's differences between that you put a stick into it first and then you add a granular object and you just poke the stick into it? Do you think there's a difference?
I think there will be a difference.
Okay, and what if you change the shape of the container, but the bottom surface area is the same? Will you think that how will it affect the results?
I think it will measure the result of the tight of it. Because when you put it up, it will be more tight or be more outside.
Because you mentioned that you always made it into a most tight situation, right? So do you think the shape of the container will affect that?
I think so.
Okay. What do you think?
I think there will be not the same since the side area is not the same. Only you say only the bottom area is constant, right?
Yeah.
But the side area will not become.
Well, the same length, right?
Yes.
Okay. And I also asked the reporter how to separate the situation in your graph into A, B, C, since it's not so clearly in the graph that we can understand. Yeah.
For A is that if our experiment does this,
Can you quantify the places that you separate it?
like this. The one is then the red line will be A, and the down red and red will be B, and the middle of our red and red will be C.
Okay. And also that, did you consider to use, like, you only use a stick, right? And what if you use a spoon, but you dip into the same depth as you did in a stick? Do you think it will, how will it affect?
The first one that we used to choose to calculate the theoretical value won't be the same.
And how, if you use like a spoon and a chopstick, which one the friction will be bigger? If it's the same material that made the spoon and the stick.
I think the spoon will be bigger.
Okay. Okay, this is good. Thank you.
Okay, so reviewer, now you have 2 minutes to prepare your talk.
Okay, well, I am the reviewer from Team of Local, and today I'm going to talk about rice kettlebells. So this is a problem signal in the test that we think we should make. So these are the pros and cons of the recorder. In the experiment, they have a
force diagram to show the friction, to draw the frictions, and also clearly define the experimental method and compare statistics. And they also made a hypothesis of the results. But the cons there are, they mention a lot of sources, but they only compare some of them, and they can consider more variable since the public statement mentioned a spoon as an example, but they use a stick. And also the ABT sections separated are unquantified, and also the type situation of the vessel is unclear. And also they didn't have experimental pictures, and the unit of density of the particle seems to be strange. And for the opponent, the pros are that they mentioned about the variable of different shape of granular object, and mentioned the lack of quantitative results for the kinds of frictions that are mentioned. And the cons are that they focus too much on the example granular material, like the rice and the thing. And I think they can discuss more other things beside the experiment setup. And for the discussion part, they said why to press the vessel and how to make sure the tightness is the same. And the reporter's response is that to make the situation tightly, and they press it until they cannot press it anymore. And we slightly agree with the reporter that we have to make the situation tight, but we think that we can use the vibration motors to control the time of the vibration as a variable, since pressing is not easy to quantify. And also that the opponent asked, can you predict that there will be more error if we change the material into rice? And the reporter's response is yes. And we agree with the reporter that the friction will be more unstable since the contact area is more unstable because of the shape. And our question is, what do you think will happen if we mix different sizes with the smaller sizes? And our opinion is that the friction can increase because the small particles can fill the space between the bigger ones. And so we agree with both of them answer. And also we asked that, well, there's a difference if we put a stick into it first and then we add objects. And the reporter's answer is yes. But we think that as long as they mention that they both press it tightly, it won't affect too much because the tightness situation will be like similar because there must be deviation. So I don't think that putting the stick into it first or later will affect this much. And also that we asked, do you think we will get the same data if we change the shape of the container, but the bottom surface area is the same? And the reporter's answer is that affect whether it is tight or not. And the opponent's answer is that the side area is the same. And our opinion is that if the angles of the container is too much, that cannot. There will be more space there will be more space if the size of the particles is bigger than the angle. For example, if we use a rectangular container, the friction will decrease. So we have to add the height to the vessel. And for the short question, the opponent asked that why did they choose to use silicon dioxide, and their answer is that because it is rounder. And we agree that when the shape is rounder, the friction and the contact area is easier to calculate and to predict, because when you have a rice, the contact area might be different when the angle of the rice is placed is different. So we agree. And also that the opponent also asked about the main parameters in their experiment, and the reporter said that is the diameter of the material and also the diameter of the vessel, which we think they can be more variables in the experiment, but we agree that these two are the parameters in this experiment. Thank you.
Okay, so reporter, please conclude the remarks.
Before we put our stick and it will have a force chain. We push our force chain to make it tighter. When we put our stick in, the stick after we put the stick in, the force chain will change. So we will press another time to make the first change, tighter. And the third thing we want to say about is, I forgot. Okay. Thank you.
Okay. Now questions. Okay.
So obviously, it's very important to use granular materials. But I'd like to listen to your answer about what's the key importance of using this granular material instead of just using water.
What?
Just the importance of using granular material. What's the key to it?
I think because there will be like irregular placement, and also because of the friction. When we use a granular material, the friction will, yeah. For example, if we use a rectangular thing, there will be like a slit between them, so there will be less friction.
Or just to rephrase the question, in your experiment, did you actually measure the change of packing density as you put in your spoon rod?
In my experiment,
In your experiment, I guess you all do experiment.
not me, my teammates.
We only try stick. We didn't try spoon because we think that if we use a spoon, we will consider a lot of force. So we didn't use spoon.
Did you measure the change of packing density?
Can I use what? I just throw little things. In our opinion, if we use spoon, for spoon it's like this. So the force when we pull up the spoon, the force will be, there will be more force than we will consider. So we think that it will be hard to calculate, and so we didn't do this experiment.
Okay. So maybe I can ask a quick question. Just a quick question. So if everything is the same, you just replace your chopstick by like a fork. Okay, let's say I use a fork. Then, because your relationship now shows parabolic. Okay, you have proportional to the h squared, right? If you look at your formula, you have parabolic curve. So if I place the chopstick by the fork, then do you think the relationship is still the same or not? If everything is the same, okay, just change the stuff you plug in.
I think it won't be the same.
Won't be the same. Why?
Because the fork isn't just a stick. It will be a plate here and it will be more pressure.
Okay, so you two,
I think
the same or not the same? And why? Okay.
because even if we serve rod, the arrangement of rice is complex to observe and measure, and in the fork, this phenomenon will become more stronger and more complex to observe. So I think it will not work.
Okay.
We think it will be different because the contact surface is different for a chopstick and a fork, and also the material that made the chopstick and the fork is different, so the friction coefficient might change. But the theory will be like similar, but the result will not be the same.
No, you say the theory is similar means it's
No,
still
I mean,
proportional to square of h squared. Or
No,
not?
it will still be the parameters will still be the contact
Okay.
surface and also.
But the relationship is different.
Yes.
Okay. Do we have any question?
Not enough time.
Okay. So maybe let's show the score. Okay. So score for the reporter: 6, 6, 4, 7, 7. For score for the opponent, 7, 5, 6, 6, 6. Okay, so the score for the reviewer 7, 7, 5, 7, 8. Okay, so let's have a 10 minutes break. Start the final round of the fight. So, reporter, you have 5 minutes to prepare your presentation. Oh, okay. So please your name. Okay, for the presenter. Actually, you can start earlier. You can start earlier if you are ready. If you would. Okay. Okay.
So the problem statement is that if you direct an airflow onto a rotating disc with holes, a sound may be heard. In this part, we mentioned that the condition to create a sound is that airflow and rotating disc with holes may create a sound. So we just need to explain this phenomenon and investigate how the sound characteristic depends on the relevant parameters. So the target is to find the characteristic of sound. And this is our observation video. We didn't blow the air through this, but we will blow it on the outside, the outer side of the rotating disc. And this is a variable resistance. And in the back of the disc, there is a motor which initiates the rotating of the disc. So, so the concept is that why the sound can be here. So, as you know, a sound is a wave that is compressing and releasing air particles, and so the air flux means the area they overlap may result in audio frequency. So in this part, you can see that when an air flux is penetrating the disc, the holes on the disc with a velocity v, and the t equals to 0, and when it comes to t over 12, the air flux now will give no holes and no air is penetrating into the holes. So it will be the sparse area of the air particles, and the one that will be the dense area of air particle. And since they're dense area and sparse area, a sound may be heard. So in theoretical model and notation, the orange one is the air flux, and the green one is the rotating disc. And here's about some notation. A of x is the area overlap. L, distance between the two holes. X, distance between holes and air flux. And the A is the diameter of each hole. So, the method that we analyze the theory and the experiment is that we just analyze the area, means A of x, and we can get a function. So we just made the function after Fourier transform, and we can get a spectrum, and get a spectrum just of this area, and we'll create a spectrum that we can analyze the frequency. And so the consideration of the Fourier transform can be started from considering we have the equation of the A of x, considering that x is between a and L minus a. And we can expand A of x as a Fourier cosine series, since cosine series is a even function. And in this way, that is also an even function. So we can just expand it for a cosine series, and the formula looks like this. And which we need, which in an is integration. And we need to get this integration solution. We can do integrating by parts. And this is the final result we can get. So mind that there is dA of x, and which we need to change the term into dx. So obviously that dA of x is looks like this, and then dx. So now we just make this into the integration. We get last page. So we'll get that, and we just make z 2 pi n a over l, and that's the function we get now. And we can represent an as an integrated form, and we just define a function of s of z, which s of z is like that. Since there is only a numerical solution of s of z, so this is the graph of s of z. That's very simple to show you. So this is the final phase we got. Since we got an in the s of z form, we just take an into the Fourier cosine series we get. So we will have this for the final phase. And as you know, that x equals to r omega t, which means here, omega is the magnitude of angular velocity of the plate, r the radius of the plate, the whole radius, and we just make it into it. And first, since that you know that cosine omega t, this omega prime t, the omega prime is the angular frequency of the harmonic sound, so we can get the final result like this in theoretical. So now we will need to prove it in an experimental process. So this is our theoretical conclusion. The A of n looks like this, and the f of n equals to looks like this. So we could expect that it is proportional to the angular velocity, which means the rotational speed of the disk. So as you know that this may represent the amplitude of the wave, and this may result in the frequency. So this is the relative amplitude in getting theory, and this is the frequency. So this is our experiment setup, and in other slides there is a motor and a variable resistance in order to change the rotational speed of the disk. So this is a virtual model. We just let air flux moves here, and we need to measure rotational speed in order to prove our result in comparable field, right? So we use a laser pointer to just make them penetrate through the middle hole of the disk, and we can measure the rotational speed by using a camera. So this is a procedure. Dig holes, we use we just buy it, fix the center to the motor, put battery, and connect the device, measuring the rotational speed by a laser pointer, and we just record the sound by Odyssey and analyze the Fourier transform, and we just change the rotational speed and repeat. And this is the spectrum we got in 14.2 round per second. As you can see that the fundamental sound is 84.79, and in our theoretical frequency is 81.36. And here's the harmonic of this fundamental frequency in 19.9 round per second. That's the result we get. The practical frequency is 119.78, which in theoretical model there is a 114.02 hertz we get. Well, 22.5 round per second. That's the spectrum we can get. We didn't show that we just calculate the rotational speed by analyze the video we take, but we didn't show it here. So this is the practical frequency, which is 135.193, and the theoretical is the 128.90 hertz. This is the one with 23.4 round per second, and this is the final result we get, which has 131 hertz in the results. So, and compared with the theoretical frequency, we can see that it's a little bit deviation, but the harmonic shows that it may be matched to the theory we can get. So we just analyze the data. So as you can see that the rotating speed to frequency graph, here's the rotation speed on the x-axis, and this is the fundamental frequency on the y-axis. And we can see that there is a linear relationship between them, just corresponded to the theory as here. Just since the omega is here, so it's so the frequency may be proportional to the omega of the disk. Sorry. So this is the conclusion we can get. So due to the sparse dense distribution of the air particles, so the sound may be here. That's the constant of the siren. And the theory matches the experimental data perfectly, which this is the very theoretical part we can get from the Fourier transform. And this is the practical experiment that we get. So, but as you can see that the practical frequency is always a little bit larger than the theoretical frequency. So we just need some, so you can see the error is about 5% and always about 5%. So maybe the initial velocity that will impact the results. Okay, that's all of my presentation.
Okay. So opponent, now you can question the reporter.
Okay, thank you for the report from the reporter. And I would like to know that how do you record yourself?
You record some by policy.
Where it is set? In front of the this or behind? Okay.
Behind.
Do you think the distance between two balls may affect?
According to our theory, you can see that L is the distance between.
Okay, thank you. And what is the relation of the first frequency, second frequency, and third frequency?
Is in a multiple of n, which n
Okay,
is the
thank you.
n of.
Do you think there is a maximum and a maximum size of the whole time will create a sound? Maximum or minimum size of the whole time will create a sound? Do you think there is a
Create a sound.
create a sound? Yes.
So we just assume that the radius of the disk is constant and just change the radius of the hole, right? Am I right?
Do you think there is a maximum radius and a maximum radius that can create a sound?
I think that maybe since you can see that in theory there is an A in the amplitude, so we think that maybe the sound can be here, but maybe the amplitude might not be too big if the radius is too small.
Okay, thank you. And what do you think that the size of the airflow may impact?
Size of airflow.
Yes.
We in our experiment and we just didn't change the size of the airflow.
And what is the relation of the size of the airflow and the hull? Do you think the hull needs to be bigger than the airflow or smaller or opposite?
Okay, time's up. So reporter, the opponent, you have 3 minutes to prepare it. You can start earlier if you are ready.
Okay, hello judges and competitors, and thank you for the report from the reporter. And I am an opponent from D101, and today I will be opponent problem number 3, diary. And this is a problem statement. If you direct an airflow onto a rotating disk with pulse, the sound may be heard. Explain this phenomenon and investigate how the sound characteristics depend on the relevant parameters. And the next point will be the velocity of airflow and angular velocity of disk, and also the size of pulse and the numbers of pulse. And now let's talk about the pros and cons of reporters. The pros is that he has well animation of the theory, detailed introduction of the theory. And also he measured the rotational speed during the experiment. Also, he shows the graph of the experimental data, and he labeled the next step in the theory to make prediction of the results. For the cons, he didn't explain the formula, the calculation clearly in the theory. Also, he focused too much on the function of the base instead of the real data analysis. Also, the relationship between the theory calculation and the experimental data, he didn't mention much. Also, the order of PPT pages should be replaced. For the discussion that we will make will be mainly focused on the first question is, does the shape of the hose influence the experiment's results? Is the airflow passing evenly through the disk no matter what the shape of the hose is? Because for the experiments, they mainly focus on when the hose is circle. But when we change the circle to another shape, will it affect its frequency or its amplitude or other things? And second is that how does the size of the hose on the disk affect the sound? For the reporter, they only have the size of the hose is controlled. And what will be a result when we have the different size of hose on the disk? And also the third question is that how the holes are set up on the disk affect the phenomenon. Yes, if the distance between each holes are different, will they have any impact? And the fourth is there a suitable distance in different distance between the holes? Because just like they have said, I think the distance between each holes may affect, but is there a suitable distance between each hole and that we can hear? And the fifth one is the outer disturbance of the sound in static states. Because for the reporter, I think they didn't consider the outer disturbance. So I think maybe they can change their experimental setup or try some ways to decrease all the and try to decrease the outer disturbance from the environment. So I would like to invite the reporter and to discuss. Okay. So let's first talk about the outer disturbance from the environment. Do you consider it?
Do you consider it as what?
What do you think is the ratio of the signal and the noise from the environment? Is there an exact number?
I think the noise from the environment it didn't affect our fundamental frequency and harmonic frequency a lot, since that you can see a very obvious peak.
Is there a ratio between these two sides?
We didn't mention a ratio, but I think it's relatively small.
How do is there some ways to decrease the noise from the environment?
One is to do. I think the thing that we can do is to. In fact, we have measured. We can call it plane test of the spectrum. Like.
Okay, for this one.
Let me show. As you see that in every spectrum we have measured, they're here and here. It's always big. There is always a big noise, and we have measured a blend test of every groups of the spectrum to make sure that that is just a noise, since the amplitude of the related to the spectrum is
Okay.
are matching, like.
Okay, thank you. But I think there is a better solution is that you can record the sound when there is no the rotating of the disc, so we can know that what is the disturbance from the environment at first, and then after you have this result, you can minus the disturbance from the environment. Although the disturbance from the environment will not be constant, but I think it is a better way for you to decrease the deviation. Okay.
Sorry. So in my opinion, you just said you just test the environment sound without rotating, right?
Yes.
But we have measured a blank spectrum for every experiment we did, and we found that to a different rotational speed, the noise is slightly different to the amplitude and the frequency. So we do it and we just match it. Since we thought that we cannot just minus the spectrum.
Okay.
We just only compare the spectrum and to make sure that it's okay.
Okay, thank you. And so that what I have mentioned in the short question, do you think that there is a maximum ratio of the pole and a maximum ratio of the pole?
Maximum and minimum.
Yes.
I think for can I use the blackboard? So you mean in the same radius of this, right? So if in general consideration it may look like this, I will just don't mind the distance between.
Okay.
So if it looks like this, it will be appropriate to blow the sound. But if you just draw it too small like this, so I just mentioned in the that will affect the intensity of the sound. So like I just mentioned about the one. The amplitude will be small.
Okay.
Since the maximum amplitude of the small is just the A.
Okay. So do you think we can calculate this size from the formula?
No. Do you think we can calculate?
Calculate the size.
No, we
Maximum.
we find the size that we like to record the spectrum and so the A it means the diameter is a constant.
So
is a not a constant.
So do you think you need to find the maximum and the maximum radius by the formula or by the experiment?
Okay, so let me draw the maximum condition. So if the maximum condition like this.
No, I mean you need if you want to calculate the maximum radius and minimum radius, will you calculate it from the formula or from this experiment and then you get it?
I will compare with the I will just calculate in theory first and just make sure that it's right.
For this condition, the opponent disagree with the reporter because for the formula that is the empirical formula. So I think it is better to find it from the experiment.
I think the derivation of the formula is clear.
Now that is the empirical formula. That is by the experiment. Okay. So do you think the distance between two holes may affect?
This one. No.
It is what?
Okay. So you will the area of air flux is always a constant. We just didn't consider it right now.
So do you think is there a suitable size between two holes?
Yes, since if you need appropriate frequency, the length of the between two holes cannot be too short, since the the difference between A of x will not be.
Is there is that number? Is that number?
No, we didn't.
Okay. For this question,
I think this is meaningless since our target is to observe a clear.
okay,
sound,
thank you.
not-
For this question, opponent think that, for example, there are two holes and the radius, and this is the radius.
Is the I'm using
Radius.
Okay.
Okay. I think that the distance between this must be bigger than 2 radius because I want to avoid the situation in that, for example, this is the airflow.
Yeah.
So it will blow into 2 holes at the same time. And I think it will create incorrect data. So I want to...
But in every distance in the hole, you still consider it as the same?
Yes.
Okay, so as I just mentioned in there, the condition for it is x between here because, as you can see, if the air flux area is too big, the A of x will look like this. You can compare with that graph, since it is always some air flux in this situation, right? So the air flux will look like this, and not touching the zero. So I think that's still analyzable. But since you have just seen there is integrating by parts, and the condition the upper formula of the integrating by parts, as you can see that we changed it because this only suits when x is between L minus A and A, since there's 0, right? There's a 0 A of x. So it will be easier to calculate, but this is still analyzable. So we do our experiment not considering this situation, since we think that that will be hard to calculate in theory, and we cannot compare the theory and the experiment.
You agree we cannot let this kind of situation happen?
I think it is hard to measure the parameters of this in this situation, but a sound may still be heard since like this one, and this is the air flux, right? This one. The area is still different, right?
Okay.
Can you?
Okay, thank you. So, how about let's moving on to next one.
So I would like to conclude is that in maybe this situation, the air flux and the hole is covered. Maybe the difference between A of x is not so obvious. So if the air flux is not so obvious, the sparse area and the dense area there may also be not so obvious. So I think there might not be a more clearly sound.
Okay, thank you.
But this still needs more calculation.
Okay, thank you. How about that? Do you think the size of the airflow and the hose, what is the relationship? Should it be bigger, smaller, or at the same?
Size of airflow, we just consider it as a constant since.
No, I think for the hole and the airflow.
I think the different. I think many conditions can hurt the sound, but the airflow and the hole the area difference should not be so big, since it will be hard to measure.
It is need to be the same.
Not need to be
Almost the same.
The difference cannot be so big.
Okay.
Okay, time's up. So opponent, please summarize the discussion.
For discussion that we have had, and we focus on the disturbance from the environment. So for the experiment, I don't think that they have considered the disturbance from the environment. So I think that what he said, he had recalled the disturbance from the environment. So I think it's better for them to minus the disturbance from the environment next time. And also we have discussed that is there a maximum and a maximum radius of the holes? And he says yes. He said yes. The hole should not be too big and too small, and I asked him that the size of the maximum and maximum radius can they calculate from the formula or from the experiment. And they said that they will first focus on the formula, but I think because of the formula is
Okay. So reviewer, now you can raise questions.
I'm the reviewer and I have some questions to ask both of you. Can you turn to page 19? The data you get is 141. And so is this?
Oh, this is they are the same. I just calculate this is
Okay,
fundamental.
so how do you define the list?
These you can see this is 280, 141, 423, 563. So this is almost the multiple of the 141, right? So so we can be infer that this is the harmonic sound of this fundamental.
Okay, so what do you think?
just that what I have asked him in the short question, is there a relationship between the first frequency, the second frequency, and third frequency? And we both agree that it has a quantity types. It is quantity types. Yes, so I think I agree with the point.
Okay, so what's the reason the noise is made? Why?
For many complex reasons, but we try our best to reduce. Like rotating, there must be some sound. Maybe not so many, but there must be. And and the
what's
environment.
the most important?
In my opinion, just in my opinion, I think is being infected by the rotations. Since the other city, the sound recording equipment is just next to the rotational sticks in order to calculate, record the sound, right? So even the sound is not very big, it still affects a lot.
Okay, so what do you think?
I think I will agree with because although I didn't know what does the sound recorder, the distance from the sound recorder and the text bus, I think like it's better for them to like make the distance smaller. So I will agree with you.
Okay, so how do you get the frequency?
How do you get the frequency? From experiment or theory?
Experiment.
Experiment that we I have just said, we record the sound, and the other city can do a Fourier transform, and we collect it since the spectrum in our city is not very directed showing this result. So we just made the data into Excel and we just draw this
Okay.
graph.
So do you do the Fourier transform?
Yeah, just by pressing one. And
Okay, time is up. So reviewer, you have 2 minutes to prepare your talk. Okay, so reviewer, please present your report.
Hello, I'm the reviewer from
理论上是不行的。
Okay, I'm the reviewer from PF5 and today I'm talking about problem number 3, stagger. And it's the problem statement. And they focus on the airflow, the rotation disk with holes, and the sound characteristics. And this is the reporter advantage. It has a fair explanation of phenomena and observation video and well-scripted presentation. And our suggestions is they have to do more experiment and didn't measure some parts of the data and the order of the page. And this is some of the advantage of the opponent. And they have good imposing manner and find out detailed mistakes of the reporter, ask those of questions and provide answers to their own questions. And the suggestions is to, they mention a lot on the define but not the data or the claim. And about the discussion, the opponent asks, where did you record the sound? And reporter say behind. And in my opinion, you have to give the position of your record because it will actually affect the experience. And the opponent asks, does the distance affect? And the reporter say yes. And the opponent asks, does the size of the airflow affect? And the reporter didn't answer. And I think the size of the airflow will affect. And opponent asks, what do you think is the effect of environment? And reporter say the environment won't affect. They did do the measure, but they didn't put it into the calculation. I think you have to make sure it is the quiet environment because the other sound may affect the experience value. And opponent asks, will you find the maximum and minimum from the formula or experience? And reporter say we find the maximum and minimum from the formula. And opponent asks, do you need to consider a radius bigger than 2 radius? And reporter say no. And thank you.
Okay. So, reporter, please conclude the remarks.
So I'm the reporter of PF5, and here's our concluding remarks. So first, so the effect by the radius of the hole and the distance between each hole is taught by the view, and we just didn't change the distance between each hole in the same distance. The frequency will be so hard to measure and affecting the main parameters we need to find. And we compare the blame spectrum and the result. So that check, and the accurate result to avoid the environmental noise. And we have did it in a quiet place. So I don't think this affects our results very much. And in all of them spectrum, one of the sound is the fundamental, and the other, which is multiple of the fundamental, and which we can say is a harmonical sound. And in the further reviewers part, he talked about one of the questions that is about does the distance affect the result? Our reply is that since we don't know which distance you are talking about, so we cannot reply or answer to that clearly. Thank you.
Okay. So now questions or George.
I have a short question to all three of you. You mentioned that it's an airflow. So how do you think about the speed of airflow? Will it change the results? Do you have your own comment, please?
So in our appendix, we say that there is always about 5% of error due to the in our vertical and particle error. There is a positive error since we think that in the graph I have just shown there is a velocity. Oh, we have fixed the velocity, but due to we should consider the frame of reference. So I think the initial velocity just will impact the frequency in here, which we cannot only consider it as the speed of the sound. It's due to the frame of reference.
And I think if you change the rotational speed, the
I'm
omega
talking about the airflow, speed of airflow.
Oh, so do you talk about the frequency of the airflow? In my opinion, if you change the frequency of the airflow, then it may be some change in the sound of the frequency.
I think the amplitude will be greater if the airflow is faster because we all know that the amplitude may be affected by the pressure and also the amount of the air that is go through the holes at the same time. So if the airflow is faster, the amount that go through the holes at the same time will be much more. So I think it will affect the amplitude.
Okay. Any question?
They can go to page 20. Anyway, any of those spectrum. So do you have the original sound wave? This is the Fourier transform of your sound wave, right?
Right.
Right.
We have recorded in city, but we just only put the spectrum.
Have you done the Fourier transform yourself?
I didn't know the sound on the presentation. In fact, it's in here, in this slide.
So you don't have, do you have the waveform of the sound wave?
Waveform? Which waveform?
Sound wave, the profile of the sound wave. Right now, this is in the spectrum, in the frequency space, right? You have the sound wave in time.
We have recorded and changed it to this form, but we didn't put it on the presentation.
So anyway, so for the reviewer and the opponent, do you think if this spectrum is correct or not? That's the answer. It's a short explanation.
The data is correct or not?
Right. Is this spectrum sounds reasonable? I mean, correct or you or not? Just you answer, I say no. And with reason.
Because I think they didn't consider the network frequency.
And then the opponent, do you think if this spectrum is correct or not? And you answer with reason.
Because it's at multiple times on the first one, so I think it's correct.
You think it's correct?
Yes.
Okay.
So in the morning, there was a team reporting the same subject, and then their measurement of this fundamental frequency is systematically about 5% lower than the theoretical one, and in your case, it's opposite. It's 5% more. So I want to know your comments, all you three, about what would be the possible reason for that.
You mean the error? First, I need to get clear about how did they consider error is that we use the practical error minus the theoretical error.
What they get is the practical, so-called practical frequency is always 5% lower, and you are 5%
Practical
higher.
is 5% lower in every group, or just
Almost in every group,
almost.
systematically.
Interesting question.
So tell us, what do you think the reason is?
I only consider in the just what I had just said, but I think I cannot answer it.
I think maybe it's the noise from the background.
I think that is because of their experimental setup, and just like what I have mentioned, I don't think they consider many environmental disturbance. So maybe it is because environmental disturbance and the quality of the microphone and also the echo.
Okay, so if there's no questions, let's score. The reporter. Okay, so it's 7, 6, 5, 6, 6. Now for the
You show 7.
7.
Maybe just read 6.
Really?
Is this again?
There's
He
5.
said
Okay.
7, yes.
He said 7.
Okay, so for the opponent, it's 7, 6, 6, 6, 6. Okay, so for the reviewer, it's 6, 5, 6, 5, 5. Okay, so any comment for the jury?
Okay, I just think that the spectrum is questionable, because I mean, if you have a periodic pattern, if it's some wave, then you basically, if it's some wave, then it's just one frequency. But if it's a periodic pattern with different shapes, then basically you have simply just the all the harmonics that can describe the spatial, the particular shape of the pattern. But that bothers me a lot, that it has all the frequencies, and it obviously it's irregular. Yeah, it's irregular. Otherwise, because if you do Fourier transform, you need to consider all the Fourier series. Then for any regular waveform with periodicity, then you have basically all just the harmonics. You don't have all other frequencies beside the harmonics. But you have everything. It's just whole spectrum.
I probably can comment. I think the wavelength, this y-axis is decibel. It's not linear scale. So that's why you see those peaks are very similar. But in fact, these are fundamental scale dominant. I believe it's a decimal, right? It's not heating. But do you know?
I can give another comment. I mean, just like yesterday, you guys always try to present all the experiments you did. But actually, you have to present most important things. Okay, about and also the fundamental physics behind the mathematics. Okay, you guys use a lot of mathematics, very special techniques, but you always don't talk very little about the physics. For example, why you want to use Fourier series? Okay, can I use Taylor expansion or not? Why? Right? Why you use Fourier expansion? What's the reason? Right? So there's a lot of physics behind. So I mean, we are PF5, right? So don't show too much mathematical skills. So just focus on physics and try to present very important part and focus your physical point. Okay?
Yeah, actually, I mean, it's just that if you want to use math, that's okay. That's something behind the physics. But you have to use it correctly. For example, that you are showing your R squared equals 1. But I mean, you should compare, I mean, when you want to compare with experimental prediction and also your measurement. And then R squared equals 1, that means that's the perfect math, right? But actually, I mean, your result doesn't support that, but you still claim that you have R squared equals 1.
Sorry.
If you look at your
R squared equals 1. That just we plot the rotational speed. I think
yeah,
things
so
I can do
I'm saying that is that when you support your theory, that would be something that you have a measurement and you have a prediction and you try to compare them. So if you are using your math, then that's something to support your physics, right? I mean, if you have, for example, if you have R squared equals 1, that means that you have very perfect result.
I think this can be considered because of I think the biggest measurement fault in my experiment because this is actually pretty.
Yeah, that's why we can discuss later.